let's continue. So what we would like to prove is the correctness of this merging network, and what we would like to do is apply the 0, 1 property. And as I mentioned before, let's just go to the picture of these two networks. What we have to show is that if you take here arbitrary 0, 1 vectors that are already sorted, then by applying them to this network, where this fn of course is defined in a recursive way, then we should make clear that the resulting vector here, the 0, 1 vector that appears here, is completely sorted. Well, what we do in the proof is the following. We just assume that here there are R zeros followed by n minus R ones, and here there are S zeros followed by n minus S ones. Yeah. And now the problem is the following. If you apply them to Fn and here to the second Fn network, then about half of these first R zeros are fed to the first network, and about half of them are fed to the next network. Yeah. And here the same holds with respect to the vector 1. Well, if you take, for example, R and S to be even, then my assertion is that we don't have any problem here with respect to the resulting output, because half of the zeros will appear here, and so half of them are given to this network, half of the S zeros are given to this network too, and the remaining ones are ones. Yeah? And the same holds here for Fn. So the total number of zeros here fed to Fn and the total numbers of zeros fed to this second one, Fn, are exactly the same. The result will be that if you are observing here the outputs, then at every output line that's coming here together to the comparators U1 and V1 will be for the first R plus S of those, divided by 2 of those input lines will be consist of zeros. So this is a 0, this is a 0, this is a 0, this is a 0, until we find a 1, but from that moment on, only ones will appear at those comparators. And so zeros are paired with zeros, ones are paired with ones. And it means, in fact, that if you have an even number of zeros and an even number of zeros here and an even number of zeros there, then these comparators do not need to do anything. They just leave the inputs where they are. And what we get is here a big vector consisting of zeros followed by ones. The same holds if both R and S are odd. The difficult part of the proof comes where if you are trying to combine here an even number of zeros in the first vector with an odd number of zeros in the second vector. Why? Well, then there will be a case where here at an output line, let's say this one, there will appear a 0 or a 1 here and another, so the complement at the corresponding other output. Yeah, so there will be here a pair that's arriving at the same comparator, for example here U2 and V2, where U2 is 1 and V2 equals 0. And then we have to take care. Well, what happens? Before such a pair, where there is a difference, all the pairs are zeros. After that pair, all the pairs are ones. So only for that comparator it is essential to make the right choice. If we would leave it, then we would have an error here. Then here would appear a 1 and there would appear a 0. But thanks to this comparator, this is turned into a 0 and a 1 and the order is restored. So, without going, let me just go then to one of the most complicated steps to show you what happened. So here we have R divided by 2, the ceiling, plus the floor, S divided by 2 zeros, followed by 1s for the output of the first FN network, and the same holds, but then the floor and the ceilings reversed for the second output. U1, U2, UN, V1, V2, Vn. Now, look at these floor and ceilings. What is the maximum amount in which they can differ with respect to zeros and ones? If you look at R and S. Well, if R and S are both even, then these numbers are the same. Yeah? So that means that you pair zeros from the first network with zeros from the second network. And the comparators don't have to do anything. If both R and S are odd, the same happens. This equals that. Number of zeros from the first equals the number of zeros from the second one. The difficult case occurs when R is odd and S is even, or reverse. In that case, they will differ by exactly 1. So there is 1 0 here less than the 0 there, or the reverse. And that means that at the corresponding place there is a comparator that has to do some work. Okay, so this is the easy case. Now the difficult case. Let's go to the difficult case here. R is odd and S is even, or the reverse, but that goes along the same lines. Then we have U, so the output vector of the first network, giving this number of zeros, and V giving this number of zeros. The number in which they differ is exactly 1. So at that position Y, Ui is not equal to Vi. And that means that the comparator is to work. Why? Well, if we know that at that position the inputs differ, then for the remaining ones they should be equal before and after. And that means that thanks to the comparator, comparing Ui and Vi, we have a completely sorted output. Well, this proof you can see that this proof makes sense because it also shows you that every comparator could be needed. There are some inputs where the ith comparator is essential in order to producing the correct output. If you leave it out, then it's gone. And that's also a thing you have to be careful when proving the correctness of the network. You have to prove that every comparator in such a network is not redundant. If it is redundant, it would come out in the proof. Okay, I leave it to you as an exercise now to prove by using the 0-1 principle that our first insertion sorting network is correct. And that should be quite easy. Okay. We have constructed a merging network. That means we had to assume that the input vectors are already sorted. And from the fact that they are already sorted, we could make a merging network that produces a completely sorted vector. But how would you use this fact in order to construct a sorting network out of the merging network? And here I apply the same idea as before. We just assume that we have such a sorting network, and in an inductive way we build a larger sorting network from. Yeah? So suppose that you would like to build a sorting network that's capable of producing a sorted vector of size 2n from an input vector of size 2n, an arbitrary input vector size 2n. Well, this network can be built as follows. You split the original input into two inputs, x1 and x2. You feed each of them to a sorting network, but now of size Sn. So x1 is fed to the first network, x2 to the second network. Output will be two sorted variants, I1 and I2. Okay. These are sorted vectors. Now, you only need an F2n network to produce from y1 and y2 a sorted complete vector. And that's your complete network S2n. So how does it look like? You have your original input x. It's split into two halves, x1 and x2. These are fed to two of these sorting networks capable of producing, we assume that, a sorted output. Then here you have your sorted outputs, y1, y2. You feed them to an F2n network, and this is the composition of your S2n network. So without filling in the details, we now exactly know how to build such a network. And we already can derive some properties of it. Well, these networks are called the Batcher networks, or the odd, even, merging and sorting networks. And one property of them is that, for example, their depth is log square n, because it is the depth of Sn plus the depth of F2n. Well, we don't know, of course, the depth of Sn, but now we know that the recurrence relation is depth of S2n is depth of Sn plus log 2n. And from that, you can immediately derive the O of this recurrence, the corresponding depth. For S2n should be the O of log 2n. Yeah, that's a simple unfolding, of course. How about the size? Well, the size of S2n is 2 times the size of Sn plus 1 times the size of F2n. We know already what the size of F2n is. That's 2n times log 2n, because the size of Fn was n log n. And here we have the size of S2n is 2 times size Sn plus 2n log 2n. And if you make the unfolding correctly, then it should come out that the size of S2n is the n log 2 n log 2 scale. Well, is this optimal? Well, if you would like to consider it as an algorithm, then immediately you'd see that this is not really optimal, because our sequential algorithms are capable of sorting in log. And this is still n log square. But of course, it is a big improvement above the naive insertion sorting network, where we had the size of O n squared and the depth of. Yeah. Yes.
When you would implement this, wouldn't this create significant overhead because of all the recursion?
No, this is a design principle. So this gives, well, once I know how the relationship is between S2n, F2n and Sn, I can actually build such a network as a piece of hardware. So all recursion will be removed. What I do is, well, I build S2n by, first of all, building this F2n network, yeah, and then, well, in a recursive way, I unfold Sn, but that is a complete network. I can build it as a piece of hardware. So if you would like, and but I will not do it. You can do it yourself at home. You can give me a sketch of this network for, let's say, n is 6 or 8. Okay. Our next topic is a possible improvement above these sorting networks that we just considered, and that's by using the principle of bitonic sort. What's bitonic sort? Well, assume that you have a sequence of numbers, let's just for simplicity assume that n is a power of 2, and well, if you are able to point out two numbers I and j, where I is less than j, such that I is the starting point of an increasing part of the sequence until j, and j is the starting point of a decreasing point in the sequence, and well, since we have here a modular n, a mod n function, it is allowed to pass beyond the end of the sequence and return to the beginning of the sequence. If that's the case, then we say that x is bitonic. Well, if I give you such a definition, then almost nobody will understand what I mean, but it is very simple to come up with an example and give you another representation of such a bitonic sequence. Assume that you have a sequence 5, 4, 2, 6, 8, 9. Then you know that 2 is less than 6 is less than 8, and 9 is larger than 4, 5 is larger than 4. Yeah. So if you take y equal to 2 and j equal to 4, then it follows that x is bitonic because, well, if you start here with 2, 6, 8, you have an increasing part, and if you take 9, 5, 4, then you have a decreasing part. Yeah? And you have covered here the whole sequence. Taking, for example, the representation of the sequence in a circle, then well, start if this is the start of the sequence, then starting with this number here, you have the increasing part, and here you have the decreasing part. Okay? So if this was the original order, then we always can split into two parts, which are in this case decreasing and increasing. Yeah. Okay. One of the ideas now, of course, is, well, if you are forced to take here two numbers, couldn't you find a more simpler representation of such a bitonic sequence as a sequence that's composed of an increasing part and a decreasing part, of which both one of them might be empty, of course. Could you just assume that the initial segment of the sequence is increasing and the second segment of the sequence is decreasing? And yes, of course, that's quite easy, because by just applying a shift operator to such a sequence, I can always assure that a bitonic sequence starts with an increasing part and then goes over to a decreasing part. So, we call a sequence simply bitonic if we have a j such that j is the largest number in the sequence, and before j we have an increasing part, and after j we have a decreasing part. Well, note that this definition does not exclude that the sequence is simply increasing. For example, when j equals n minus 1, or is simply decreasing when j equals 0. Yeah. Okay. Then a very simple observation. Every original Bytonic sequence, where we could start in the middle, starting with this increasing part, there always exists a linear shift such that the ls of the shift is a simply Bytonic sequence. And well, that's very simple, and here is the formal definition. If you apply this simple shift, I plus k goes to k plus n modulo n, then we have here simple Bytonic representation. The most important conclusion from this observation is that, well, instead of dealing with arbitrary Bytonic sequences, it suffices to look at simply Bytonic sequences. Yeah? Okay. And there we have a very nice property. If you have a simply Bytonic sequence, so a unimodal sequence, then, and it is of length 2n, and you compare the corresponding elements from the two halves of the sequence, so S0 with Sn, S1 with Sn plus 1, and S minus 1 with S2n minus 1, and you take the minimum and you collect them in the L of S, and you take the maximum and you collect them in the R of S, then taking these two sequences, both containing half of the elements of the original sequence, we can show that both are Bytonic. So from Bytonic sequences you can obtain simpler sequences that have the same property, but there is an important relationship between the two of them. You don't have to bother about the order in which sorted variants of Ls and Rs do appear, because the maximum of Ls is less than or equal to the minimum of the Rs. So that means in fact that if you would sort Ls and you would sort Rs, then the total sorted variant of the original sequence is just the concatenation of the sorted variant of Ls and the sorted variant of Rs. And that's thanks to this property. Now, I will give you a part of the proof, and this part of the proof just assumes that if you take a Bytonic sequence as a unimodal sequence with a unique maximum, then this maximum will always appear in the second half. So j will appear between n minus 1 and 2n minus 1. Yeah? And the reverse, so the second part is completely analogous by taking j in the first one. Okay. So we will show now that these two properties hold for this part of the proof, j and n. So, well, take two cases. I just assume if you have such a Bytonic sequence, here you have it, that now Sn minus 1 is less than or equal to S2n minus 1. So the maximum of the first half, and this is an increasing sequence because we assume that j maximum is not in the first half. So Sn minus 1 is less than, the maximum is less than S2. Okay. If you now take the L of S, then the L of S compares corresponding elements in the first half with corresponding elements in the second half. Now we know that every element here in the second half is at least as large as every element here. Why? Well, here the sequence is increasing, so here before j, every element is larger than every element here. And this element is larger than the maximum element in the first half, and every element before it is also larger, so every element here is also larger. So if I take the comparison Ls and looking for the minima, then what should occur here is the L of S. These are all, well, let's say, so to see, losers in the comparison between the first half and the second half. And the winners, of course, appear here. Yeah? Now, note that the property holds. All elements in Ls are less than all elements in Rs. Yeah? And both Ls and Rs are bitonic. This is trivially bitonic because it is an increasing sequence having its maximum at the very end of the sequence. Yeah? And this, of course, is also a bitonic sequence having the same maximum as the original sequence. Yeah? And note, if I would sort both these and these, then by simply concatenating the results, I have the sorted result. Okay. Now a more complicated case, because, well, the second case should be Sn minus 1 is larger than S2n minus 1. Yeah? So this is the second case. Here I have Sn minus 1, and this is S2n minus 1. Yeah? Now it looks somewhat complicated, but let's go through it. So what I do is the following. You should imagine that we draw a horizontal line that originally crosses this graph through Sj, yeah? So the highest point. Yeah? And now I continue by lowering this point until there is a point k, such that Sk is at least as large as Sk minus n minus 1. And Sk plus 1 is not larger than Sk minus 1. So here we have this k. Sk is at least as large as Sk minus 1 minus 1, minus n minus 1. And Sk plus 1 is smaller than Sk minus 1. Yeah? So this is a kind of crossing point, so to say. And this crossing point is important because if we now make a comparison between Sk minus n and Sk, so Sk minus n and Sk, then the winners of this comparison will occur in Rx, and the losers will appear in this part and in that part. Yeah? Because in this part we compare the elements from S0 to Sk minus n minus 1 with the corresponding elements in the second half, so that will occur between here and here. Yeah. And from Sk minus n until Sn minus 1, we compare them with this set, and now the losers will appear here. So, if you take the comparison, here again, then here we have a part Ls, and there we have a part Ls, and again here we have Rs. So, what you see is that all elements in Rs again dominate all elements in Ls, and both sequences again are bitonic. Here you have a starting sequence that's increasing and the final segment that's decreasing, and this was already a part, a continuous part of the original bitonic sequence. Okay. So again, here we see that both properties that I would like to show you hold. So, in fact, now we know that you can split a bitonic sequence into two bitonic sequences, each consisting of half of the elements. So, we can use that to form a kind of bitonic merging procedure. And the bitonic merging procedure goes as follows. If you consider a normal merging procedure, then what you give the merging procedure is two sorted input vectors and you produce a totally sorted variant. What you're doing here is you are weakening the conditions on the input. You do not give them as input to a bitonic merge a completely sorted input. No, you give it a bitonic sequence. And what you would like to have is a sorted variant out of it. Okay. Well, how does the corresponding algorithm that makes use of this bitonic property looks like? Well, first you compute the number of elements. If you have only one element, then of course sorting is trivial, so you return the original sequence. If n equals 2, then what you do is you compute the minimum and you compute the maximum and you just glue them together. You make a concatenate between the minimum and the maximum, and there you have your sorted variant. If n is larger than 2, then you compare the first halves, the elements from the first half with the elements from the second half by means of this LS and RS procedure. So the L of I is the minimum of xi and xi plus n divided by 2, and the Ri is the maximum of xi and xi plus n divided by 2. So this is the same as the LS, taking the LS and the RS. You know that now this sequence L, consisting of n divided by 2 elements, and the R, also containing n divided by 2 elements, that they both are bitonic. So you can apply the same procedure, bitonic merge, on these two halves. And what you, if the procedure is correct, would achieve is here a sorted variant of the first half of the sequence. Yeah. This is also a sorted variant. But now you make use of the fact that if this is the L of S and this is the R of S, that the maximum of any sorted variant is smaller than the minimum of the sorted variant of the R of S. So you just can concatenate those sorted variants to obtain the final result. Yeah? So if you concatenate this sorted variant with this sorted variant, then you have the final result, and that should be the sorted variant of your original input. Okay, so this is the idea of applying a bitonic merging procedure given a bitonic sequence to achieve a completely sorted sequence. Now we will use this idea, this algorithm, to build a bitonic sorting network. And what's the idea? We will build a network Bn that takes a bitonic input of length n is 2 to the power k, and we will do it in an inductive way. If we have n equals 2, then of course we need one comparator to construct B2. That's simply compare the two inputs, give the minimum at the upper line and give the maximum at the lower line. Then you are there. If k is larger than 2, then you need k divided by 2 comparators to obtain the Lx and the Rx by comparing the first elements of the two halves. Because you have to split them in the minimum and in the maximum. You have the minimum of the first elements of the two halves, then the maximum, then the minimum of the second element of the two halves, etc. So what you need is k divided by 2 comparators. And you feed them by 2 sorting networks, bk divided by 2. Why? Well, you have to apply that in a recursive way, like we saw in the algorithm. And together, that constitutes a big bk network, because you can trust the outputs. If you take the outputs of the first network, the upper side, and the outputs of the second network in the lower side, then you have a completely sorted network variant. So here is the sorting network. So to obtain a Bn Bytonic sorting network, you take first here k divided by 2, or n divided by 2 comparators, each comparing the successive elements in the halves of the input. You feed the first half to a Bn divided by 2 network. You do the same with the second network, and well, the resulting output here is a completely sorted variant of your original input. And of course, by unfolding, you obtain your complete network design. So what's the complexity? Well, the depth of Bn is 1 plus the depth of Bn divided by 2. Take an arbitrary output line, and you see that, well, there is one comparator that's touching, besides all comparators that are touching this output line in Bn divided by 2. The depth of a B2 network equals 1, and that means that the depth of Bn equals the log of n. What about the size? The size is n divided by 2 plus 2 times the size of a Bn divided by 2 network, while the size of a B2 network equals 1, and that means that we have n times log n divided by 2 for this merging. So if you assume the inputs to be Bytonic, then you can sort them in log n time and with an amount of hardware equal to the O of log n. But of course, that still requires you to have inputs that are Bytonic. And how would you now obtain a Bytonic sorting network? That means that you have to get rid of this assumption that the inputs are already Bytonic. So what we now have to do is we have to come up with a network that takes an arbitrary input, transforms it into a Bytonic input, and then applies a Bytonic merging network to obtain the final result. Okay. So, oh sorry, this is of the title. So, how to extend now our Bytonic merging network to a Bytonic sorting network. So given an arbitrary vector of inputs, how to come up with an ordered variant of x using Bytonic sort. Well, what we do is the following. We apply 2 steps. In step 1, we use a sequence of Bytonic merging networks, bk, to transform the input to a Bytonic sequence with length n. So that means that we try to comply to the prerequisite for Bytonic merging, that you have a Bytonic sequence. And then in step 2, we apply a Bytonic merging network, Bn, to sort the output of step 1. And now the nice thing is that for merging and sorting, you are using the same type of networks. So there's no longer a difference between sorting and merging. So how to come up with the final result? Well, if you have an arbitrary input, you distinguish you distinguish in it subsequent elements that constitute a sequence of 2. So every sequence of 2 elements appearing in your original sequence are by definition bitonic. Either x is less than or equal to y, or the reversals. Okay, so every sequence can be seen as a concatenation of bitonic sequences of length 2. So divide your original sequence in elements of 2, and you have a sequence of bitonic elements. Now apply first n divided by 2 B2 networks in parallel to these pairs of elements from X. And ensure that successive pairs are sorted alternately. So increasing and decreasing. By means of which you are forming larger bitonic sequences. So here is the idea. Here is your original sequence. Split them up in pairs and then feed these pairs to bitonic networks. And now we distinguish 2 variants of these bitonic merging networks, a plus and a minus. A plus sorts increasingly and a minus sorts decreasing. Well, if you take the output of 2 of these networks, so a plus and a minus, then you have a bitonic sequence of length 4, isn't it? Increasing, decreasing. Then again, you have a plus B2 and minus B2. Again, you have a bitonic sequence of length 4. Here you have bitonic sequence of length 4, and you have a bitonic sequence of length 4. So, from the input, it's very easy to come up with bitonic sequences of length 2 and length 4. How to continue? Well, the idea now is simple. In order to form here bitonic sequences of length 8, what you have to do is to apply them, to feed them to here a plus B4 network and the second half to a minus B4 network. That gives you a total of a bitonic sequence of length 8. And you continue until you have a bitonic sequence of the original length of your input. So, what happens is the following. Let's do it for n equals 16. Here, you form bitonic sequences of length 4. Yeah. You feed them to a B4 plus B4 network. This half to a minus B4 network. This again to a plus B4. This again to a minus B4. The output now, of course, is in total a bitonic sequence of length 8. You feed it to a B8 network, and this one to a minus B8 network. The result will be a bitonic sequence of length 60. And this is a transformation of an arbitrary input vector to a bitonic vector of length 60. Now, to obtain the final sorted variant, you feed it to an increasing B60 network. What does this network? It is a bitonic merging network that, if given a bitonic sequence of length 60 n, produces a total sorted variant out of it. Yeah. So what you see here is that you can build a bitonic sorting network by using as elements a bitonic merging network. Okay. Well, look at this picture now to come up with a computation of the cost, that means the size and the depth of such networks. So, what's the depth? Well, the depth of such a sorting network consists of the depth of a B2, the depth of a B4, the depth of a B8, the depth in general of a B to the power log n network. In order to form this resulting sequence, bitonic sequence, and as the last step, applying a and merging network to obtain the final result. Well, if you count, that is the depth of a B2 is 1, the depth of a B4 is 2, so this 1 plus 2 plus 3 plus log n, and that's the O of log square. Yeah? Okay. What's the size of the BSN network? Well, that's n divided by 2 times the size of a B2 network. There are n divided by 2 pairs. This is n divided by 4 times size B4, plus, in general, n divided by 2 to the power I size B2 to the power I. Yeah. If you compute that, it is the sum of course, here you see in the exponent log n, y is 1 to log n of n divided by 2 to the power I, 2 to the power I log 2 to the power I divided by 2, and if you compute the final result, it turns out that this is the O of n log square. So in this respect, we achieve the same result as this even merge networks, where we also had a depth of log square n and the size of n log square n. So summarizing, if we take Bytonic sort, then, well, the time we need to sort is log square n, the amount of work is n log square n, not weakly optimal. Odd even sorting networks achieve the same profile, but how about an optimal network? We would like, of course, to achieve a sorting network that is weakly optimal with respect to serial algorithms. And here the bad news is that indeed there exists a network that's weakly optimal, but the nasty thing is that if you would like to build such networks, you need networks of galactic size. That means that for approximately n equal to 2 to the power 78, then such an AKS sorting network, an optimal network, will have the same size as an odd-even sorting network. And below that, you can simply forget it. So it means that the constants here that are involved in log n and n log n are so high that they can't be applied practically. So we can build optimal networks, but indeed for very, very, very large n's, they become superior compared to odd-even sorting networks and to Bytonic sorting networks. And recently, that means last month, we have seen some publications that try to reduce these constants below this n 2 to the power 78, but not many progress has been made. So we have to wait until you have finished your studies to improve it. Okay. Next week is the last lecture. I will briefly deal with 2 graph algorithms before the break, and after the break I would like to show you, well, let's say a kind of test axiom and discuss the solutions to it in order to give you some idea of what you can expect the week thereafter when the final exam